All right, so wow, we're down to a handful. Okay, so oh, I don't even need to tell you a joke to quiet you down. Do you want a joke? Would you rather have a story? Story? Who wants a story? Yeah. All right. Okay. So I don't know. This one's kind of okay. A student of mine, a former student of mine, who went back to his home country, which I'm not going to tell you where it's from, a few years ago, because he's committed to going back because he's a patriot, and so he came over and he's visiting me, and we went to the bar, and I complained about my miserable life or whatever, and he's like, "Yeah, what have you been doing?" And he's like, "Well, I've been doing expert testimony in court." And oh, really? You're doing? Is that to make some money on the side? He's like, "Well, I don't really get paid," and he said, I was like, "What? What do you do?" And in this country, which I'm not going to name, probably I should even have the tape taken off. There's some rules against speaking against the leadership of the country, and he's a computer scientist, so he helps people who are, they run message boards or newspapers, and he testifies to some of these message boards or chat rooms people can post, so you don't really know who's posting, and there's laws about them taking down stuff quickly about if it says something bad about the leadership, you could get in trouble as the webmaster, or as if they're in your comments on your newspaper, you could be in trouble. So he testifies for these people who are charged with this crime, and I was like, "Oh, how's it go?" And he said, "Well, the last one I testified for got 13 years." And so anyway, it's sort of, I stopped complaining. So, okay, that's my story. So, yeah, I'm very proud of him, right? He said, "I may have to flee the country." I was like, "Yeah, sure. You stay in my house whenever." So, okay. So I'm just bragging about my student at this point. Okay, so we're talking about maximum flow. Okay, so this is the problem. You have a flow network. You're given a graph with vertices, a set of vertices and a set of edges. Okay, and now they're directed edges. Okay, from U to V. Okay, so it's often called a flow network, and that's why. Okay. And the network also includes a source S and a sink T, and capacities that are greater than or equal to 0. Okay, I lost an equal there. Okay, so this is an example of a network. Okay, so there's a source S and a sink T, and there's a number of nodes and edges, and there's arcs with capacities. Okay, and so what you want to find, this is the input, is this network. What you want to find is a flow assignment to all the edges. You want to assign a flow value that's less than the capacity, and flow values should be positive or non-negative. And if for any node in the middle, like C, for node C, for example, you want the flow in to equal the flow out. Okay? You don't want flow to be created or destroyed in the middle. Okay, the flow always starts at the source and should end at this sink. So you might think of a flow as sending a unit from S, one unit from S to C to E to T. But another way to view it is on each one of these arcs, I'm going to send 3 units on S to C, So I better somehow send 3 units out of C. Okay, that's what this conservation constraint means. Okay, that's what the excess doesn't build up there. Okay? Okay, so this is the idea. Do people understand this? So this says the flow in for each arc coming into U, the total flow in for every arc, you add up the flow in. For each arc going out of U, you add up the total flow, and they should be equal. Okay? So that's what defines a legal flow. So there's these 2 constraints. I call them capacity constraints, and I left out the labeling, but this is a conservation constraint. Flow is conserved. It doesn't, there's no corruption in the middle where stuff is stolen. Okay? It's all at the endpoints. Okay? Okay, so is that clear? Now what do you want to do? Here's a feasible flow. A good flow is just all zeros. A zero flow is fine. It's a solution to this problem with just these constraints. But we want to maximize the total amount of flow that goes from S to T. And so what we're going to do is we're going to maximize the flow flowing out of S. That's what this particular sum does. It tells us the flow coming out of S. Right? So if you sum all the arcs coming out of S, of the flow values, that tells you how much flow leaves S. Okay, and where does that flow go? Where must it go? Yeah, it has to go to T, right? Because it can't end up anywhere in the middle. So if you can follow one of those units to all that flow, it goes somewhere, and then from all those nodes it goes somewhere, and from all those nodes it goes somewhere, and eventually it goes to T. Okay? So there's sort of lots of ways to view this, right? If you so you could have maximized this. You could have defined the size of F to be the flow going into T, which is going to be the same value as the flow coming out of S. Okay? Okay, so one way to view it is you could say, for each arc, you can make this equality sign a minus, and you can make it equal to 0. Okay, then it looks like a linear program. Right? Okay, so, and one thing about these kind of, if you added up all these equations, all of them, all the capacity equations, each edge would appear twice. Once as a negative and once as a positive. Okay, so the only thing that you would have left that didn't appear as a negative and a positive is the source and the sink, and so they would cancel each other out. Okay? So that's one way. We have this intuitive understanding, well, flow comes in and flow comes out. It can only end up at the sink. But you could also write it out as equations and just say, well, for every arc, if its endpoint is C and E, for C, it appears positively. Or, yeah, if you make this a negative, it appears negatively. And for E, it appears positively. So if you add up all these equations, everything cancels, and that's except for the flow out of the sink and into the source. I mean, the other way around. Okay? So, so this is a flow. Okay, let's check if it's legal. So all the capacity constraints have to be satisfied. So we'll check one of them. Let's look at this arc. So that's what it means for it to be satisfied. Okay, the blue is the flow. The black is the capacity. So 3 should be less than or equal to 4, which it is in this flow. Okay? Another constraint is this capacity constraint. You want to show that the flow into C, which is, there's only one arc coming into C, right, FAC, and that has value 3, should equal the flow coming out of C. And what is the flow? What are the arcs that leave C? FCE and FCD. And so the total amount of flow on FCD is, I got it reversed, but is 1. And the flow coming out of FCE is 2. Okay, so these values are equal. Okay, so we could do that for every node and every edge, and we know we have a good solution. Okay? Okay, so again, another good solution is all zeros. So what we really want to do is we want to see if this size is maximized. Okay, so let's just actually calculate the value. What is the value of this flow? Again, we sum up the arcs coming out of the source, and that gives us the total flow. Okay, 1 plus 3 equals 4. Okay, so who thinks this is an optimal flow? Okay, why? Okay, so what he said is, he said the following. Okay, he said, look at that cut. Is that the cut you said? Yeah. Okay, so if you look at this separation, let's look at the black numbers here. Okay, there's a 1 plus a 1 plus a 1 plus a 2. What is that? 1 plus 1 plus 1 plus 2. 5, right? And the flow is 5. Uh-oh. Uh-oh. What did they do wrong? Yeah, this, in some sense, let's think again about this whole infrastructure, okay? So what we want to say is we're trying to route flow from S to T. Okay, so now if you think of all these nodes on this left-hand side and all these nodes on the right-hand side, and you just sort of collapse them, you have to route, to get flow from S, the little node S, to the little node T, you have to get node from this flow from this whole set of nodes to this whole set of nodes dt. And it has to go across, the only edges it can use to get across there are these edges, A to D, C to D, E to T. It cannot use E to D, right? That is in reverse, yeah. Yeah, that's, I'm saying I shouldn't have. I shouldn't have added D to E. Okay? Is that what, okay, so I'm just, so why, so the total amount of capacity from this side of this cut to this side of cut is 1 plus 1 plus 2. This D to E is not useful for sending flow from this side of the cut to the other side of the cut. Okay? So the total capacity, I know there's no flow. There's not going to be any flow at all, and I'll prove this a little more carefully later. But intuitively, there can't be any flow from this set of 4 nodes to this set of 2 nodes that's larger than 4, right? That's the total amount of capacity that goes from this side to there. Okay? So that says I can't do a flow that's bigger than 1 plus 1 plus 2, which is 4. This flow has value 4. So if I have an upper bound saying I can't do better than 4 and I get 4, what must my solution be? Yeah, it's optimal. It is optimal. So the point is it is optimal. Okay? So because this cut size is 4, any cut gives an upper bound. Okay? So that's the key. So yeah.
So if you have optimal flow, does that mean when you look at this cut, all the edges will be at capacity?
Yeah. And we'll prove something like that later. He asked, if you have optimal flow, will all the edges across the cut in the right direction be at capacity? And the answer is, for an optimal flow, yes, right? That's the total amount of flow that goes from S to T, is the flow that goes across the cut. For any cut, the total amount of flow that goes from S to T. If you make any cut here and you add up all the flows across the edges, that is the flow that goes from S to T, because it can't end up anywhere else. It has to end up at T or start at S. Okay, so any cut gives an upper bound. Okay, so again, this is what we want to do. We want to find a flow with under these constraints. So notice it's a linear program. Okay, so this is, I'm just kind of reviewing this stuff, but it's a little bit subtle, so I want to do it again. So the variables are f of e. These are variables in my linear program. The constraints are linear, right? The constraints of the form 1, the capacity constraints are linear, just says each variable is less than some number. The CEs are numbers, that's input to your program. The FEs are variables. Okay? So the C's are an input, and you just have a right-hand side. And the second one is the conservation constraint. Normally, your right-hand side is a constant. So you may want to write this, if you're going to write out a linear program, you might want to write it out as the sum of f of u w minus the sum of f of u. Right? So then the right-hand side is 0. Okay? Appropriate u. Okay? So this linear programs, linear constraints, linear optimization function. Okay, so that's cool. The optimization function is you're maxing a linear sum of the variables. So you can just use a linear program and solve this problem. Okay. Okay. So linear programs are kind of, kind of complicated. So let's see how it works. Okay. We're going to try to solve it directly. So it's sort of like the simplex method, which briefly is the method that Christos drew, and you did in high school, where you draw this feasible region, and then you sort of move around the feasible region to find better and better solutions. So the simplex method is a method that does that, and this is how it looks in a graph. There's a combinatorial interpretation of it. Okay, so you find an S to T path. So what you do in each step is you find an S to T path with some remaining capacity. You add flow to the variables along the path. You add some fixed amount of flow to as much as you can, and then you update the remaining capacity. So we could look at this this example here. Okay, so here's say I'm doing depth first search. Maybe this is my path. This would be my path if I was doing depth first search, right? With lexigraphically. Okay, so I found a path. So you can use depth first search to find the path. We know how to do this. Okay, so now I want to change. Right now, all my flow variables are 0. So what do I need to update them to? What should I update them to? What do you think? 1. Okay, well, okay, 1. Why 1? Yeah, okay, so you want to route, essentially, intuitively, you want to route flow along this path, and you want to route as much as possible. If you route more than 1, you're going to violate these capacities. So you route as much as possible, so you update your flow variables, and you update your remaining capacity. So it used to be the capacity was 4. After you route 1 along this path, the capacity is 3. Okay? It used to be the capacity was 1. Now the capacity is 0. Okay? And the flow variables I'm keeping here too. Okay? And so on. The capacity was 1, now it's 0. The capacity was 2, now it's 1. Okay? So we keep doing this. So already Christos showed you an example where there's a problem here. Okay? So where's my uh-oh? Okay? So let's look at it. Let's look at it in a simplified setting. This particular move we made is going to not lead us to the right path. Okay? So we're going to have a problem here. And let me show you in a very simple example where the problem is. Okay? So we're going to run this algorithm again. So we're going to find some path, which is this path. Again, depth first search would do this if it was lexicographic. Okay? So you find this path, you do this algorithm. By some miracle, I got all the moving parts working. and so those are the correct things. This is the remaining capacity on this edge is 0. The residual flow, the flow on this edge in this direction is 1. The amount of capacity you have left here is 0, and so on. So now can you find any path from S to T? Okay, do you think this is the optimal flow? Okay, so this is a miracle. Okay, this is the first thing we're going to do. It's going to be something where we're really going to do something that's not greedy. This was the greedy algorithm. Okay, this is like, let's just route as much flow as we can along this path and see what happens. And usually, we have these not greedy, and then if that doesn't work, basically, often nothing works. But for linear programming, something else is happening. You can actually deal with this. So does anybody remember how Christos dealt with it? Yeah, he's saying it out there. He's doing this. He's saying, okay, well, in some sense, let's think about a little unit of flow. Okay, instead of trying to find a whole path, let's just think about what a unit of flow can do. Okay, so a unit of flow starts at S, it can't go out to A. Okay, but it can go to B, so let's just let it go to B. Okay? So it's up here and it's hanging out, so oh darn, I can't go anywhere. Okay? But in some sense it thinks, well, you know what? I'm going to steal this guy's thing. Maybe. Or I'm going to, because a unit of flow is coming in here and going this way, right? So I have a unit of flow here. I could say, hey, you, don't come. Okay? Don't come. I got you. I'll handle this outgoing flow for you. And this guy goes back up to A, and now there's a unit of flow at A. Okay? And then from A, you can send that unit of flow to T. And everything works. What you've done is you've increased the flow here. This unit of flow traveled along here, use that capacity. And then it told this flow, don't even bother coming here. And he unuses this capacity. Right? He says, okay, don't come here. So that actually unuses this capacity. And then now from there, that unit of flow, there's a unit of flow there that says, oh, I can go to T this way, and you can use that capacity. So, so that's kind of a little picture of what we're doing, right? But it's kind of a weird algorithm, little things walking around like that. So we're going to instead, and we know how to use breadth first search. We know how to find paths in graphs. This whole walking around stuff is not what we normally do. So let's code up this intuition into the graph structure. So the way we're going to code up this intuition is if we ever pushed flow along an edge, we know that if flow comes in some way here, we could reduce the amount of flow that came in here by the amount. So there's too much flow here. So we want to reduce the amount of flow that came in here from somewhere else. So we could do that by reducing this arc. And what that does is actually makes this unit of excess go from here to there. So it makes a graph, it sort of looks like we're searching. We're moving this excess here, then we're moving the excess to A, then we're moving that excess to, what is this one? T. Okay, so what we want to do, since we can move in this direction, we can move this unit of flow in that direction. What we want to do is we want to actually add an arc in that direction. It says we can push flow in that direction. We could push one unit of flow in that direction by just undoing this flow. Okay? So the way we code that up, okay, this, optimals 2, this was, we add reverse arcs. Okay? So we take our network, and this notion of updating the remaining capacity is a little more subtle. The easy part is if you had a capacity of C, and you route 1 unit of flow, you have to decrease the capacity by 1. That's the first step. Reduce, we'll call them residual capacities. So REs are the residual capacities. It's how much capacity I have left in that arc. So in this arc, I have 0 in this direction, residual capacity. because its capacity was 1, and I subtracted 1 from it because I already routed a flow of 1, so I can't push any more flow along this direction. On the other hand, I could, if a flow comes in here, I can push flow in that direction. So I'm going to add a residual arc in that direction. Basically, all the residual arcs are just reverses of regular arcs of capacity equal to the flow, because that's how much flow I can push in that direction. So I'm adding an arc, I'm adding reverse arcs to indicate this reverse capacity. Okay? So, has anybody seen an algorithm like this, where you do something and then you undo it and you do it and you undo it? Yeah. 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 Yeah, that's true. I mean, I guess, I don't know. That's not what I meant for the answer to be. But in some sense, this is something we kind of did in grade school. Okay, there's this whole notion of solving linear systems, right? You have this variable. If you raise this, you better lower that, and then you better raise this. You better lower that. You don't. It's not greedy. You don't just say, okay, let's put in these values and have it work. You actually have to do an algorithm. Right? You set something, and then you're like, okay, well, it gets undone and done. Gaussian elimination is one of these really, really fancy algorithms. Okay? It's one of these things that is not greedy. It's just you follow these rules and things happen. And really, linear programs are embedding Gaussian elimination. This whole moving along lines that you see in this feasible region, where your Christos drew this picture last time. What you're saying when you move along this line, when you're trying to increase x1, you better decrease x2. Okay, that's what's happening here. If you increase the flow into here, you better increase the flow out. So this is this linear equation that's working for you, right? That's what you have to obey. Okay, so that's how it comes from these linear programs. Okay, so this is a very nice algorithm. People came up with it without linear programming. But what's really going on is something about trying to force the satisfaction of these inequalities here. Flow in equals flow out. How do you satisfy it? You raise this variable value. You better raise this one, otherwise you're not inside the feasible region, right? Because these two have to add up to something. In this case, 0. Okay. What comes in has to go out. So increasing this variable better mean you better increase this variable. But if this variable is already high, if you increase this variable, you can lower this variable. Okay? So this is I love flow. I'm sorry. Okay. So then what happens then? So then you add this reverse arc, and now so you add these reverse arcs, and that's a little off pink. So now can you find a path from S to T in this network? Does anybody see a path? Yeah, so you can go along this arc. You can go from S to B, from B to A, and A to T. Okay, so now what happens when you actually augment flow along here? So augmenting flow along here is the same as it was before. You're adding 1 unit of flow, you get a 1 there. Okay? And the remaining capacity used to be 1, now it's 0. Okay? For this arc, in this direction you have capacity 1, so pushing flow along this direction is the same as decreasing the flow along this direction. So I'm pushing 1 unit here. I had f of e really was a variable that went from there to there, and it said 1 unit is flowing from here. Now I want 1 unit to go that way. So it's subtracting this 1 from here, and then I get no flow coming here. And then my residual capacity, since I used to have a capacity of 1 and coming in this direction, and I have no flow on it, that's the capacity. Okay? So, and then this other edge is more or less like it was, like the same as this. It has capacity 1, you're trying to push 1 unit of flow along it, so you decrease its capacity by 1, and you increase its flow by 1. Yeah. Yeah, you don't. I mean, at least the flow gets bigger, so it ends, right? That's something, and we'll talk about a reasonable amount of time. I mean, it gets bigger by 1 every time at least, right? So it gets bigger by something. Okay. So like what's one, instead of doing depth first search, what's another algorithm? Breadth first search is another algorithm, but if you think about it as I want to augment as much flow as I can in each step, what's an algorithm? Did you guys do bottleneck path? Did you guys do the bottleneck path problem? Okay. So it's sort of, so you want to find the path with the highest minimum capacity. That's one algorithm to make it go faster, because then you're at least routing as much flow as possible along any path. And that may terminate faster. And you can prove bounds for that, but we're not going to do that today. But that's one example of what you might do intuitively. Okay? But here we're just using depth first search, which is, as you see, bad. I mean, can be bad, but at least it works, right? Now we're done. Okay. Well, I mean, it proves, it does something, right? We got some answer. So let's just do a big example here. Okay. So this is always a challenge. Okay. So you add. Okay. So this is what we've done so far. And now those other arcs, the reverse arcs, are too much to draw on here. So basically I drew, when you have a residual edge, I drew arcs in both directions. Okay? So if you have a residual capacity in this direction, if the arc came in this direction and you have a residual flow, you have a flow along here, you have capacity in the opposite direction. I actually changed this later. Okay, so now you can find, so here's my first augmenting path, which is the one I had before, from S to A to D to E to T. Okay, I'm starting there. Now I can find another augmenting path, which is fine. I find one, and then I get some mess. But the same thing happens, right? Here I'm routing 1 unit of flow, so this one goes from 3 to 2. I have a bug here, and so on. The 1 unit of flow, so it goes from 4 to 3. Wait. Okay, so I think I have my things. Okay, this is the right one. Okay, so there you go. So that's it found this path. It adjusted. The green arc says the reverse arcs are in. Okay? Okay, so what's another path? You guys see another path in here? I just showed it. But do you see another path in here? This one's interesting because this one is actually, it's using residual capacity here. Here there's capacity 3, so it's allowed to go. Here there's capacity 2, it's allowed to go. Here this is a reverse arc. It's allowed to go because there's that green arrow that says we're adding in this residual capacity in the opposite direction. So we made a mistake here with our first depth first search. We need to fix it in some sense. Okay? And then we can adjust it again. So now we have a flow of value 3. So there's one more path here. They're not always easy to see, but there's a residual capacity here, residual capacity here, residual capacity here. And now it's a value 4. Okay? Okay, so is that the optimal? So first of all, let's check the results. So this is our thing. The capacity constraints. Again, this is the flow we started with, so the checks are exactly what I did before, but you can do them for every edge. Okay? And now the question is it maximum size? And here again, we have to check for the optimality. And there's this cut thing. Okay? So we know, in this case, we see that we got a solution that obeyed all the constraints. But really, for an algorithm, we need to prove it. We need to prove that it obeys all the constraints no matter what. Okay? And we need to prove it's optimal. So in this case, it is optimal because there's this cut that tells us it's optimal. Okay, but are we always going to terminate with such a condition? That's what we need to do to prove it's optimal. Okay? So any cut gives an upper bound, and so then we know we're optimal. Okay, so let's look at the correctness. Okay, so so we have capacity constraints, which are these. We need to make sure all of our FEs obey the capacity constraint. So on any arc, we only increase the flow value to C of E. We force that, right? We keep removing residual capacity if there is, until if the flow value is C of E, we don't route any more flow on it. Okay? We find a path, and we only find a path with positive residual capacities, and we only push through the residual capacities amount. So that's fine. Or we use reverse arcs. Now, reverse arcs, we throw in these arcs that weren't there, but we only can use them to make the flow go down to zero. It never becomes negative. Okay, so all the flow values are positive. So flow values are between 0 and CE. Conservation constraints. Okay, here, why is conservation obeyed? Because you're always using a path. So you need to say the flow into and out of V is the same. Okay, so the algorithm adds flow along a path. So when you add flow along a path, what happens for every vertex in the middle, well, every vertex like this, actually. So you add flow to some vertex U. So you may add one here and add one here. Since you add one to this and you add one to this, then this equation remains satisfied. Okay? Unless it's S or T, that's what you always are adding flow coming in and flow coming out. So the equation is satisfied. Okay? So each internal node has F flow in and F flow out. Right? If you add F flow along the path, you're adding F to this sum and you're adding F to this sum. So the thing goes to 0. Okay, so that says you've obeyed all the constraints. Okay, so now you want to show that it's optimal. Okay? Okay, so I'm going to now prove this upper bound on the min cut. Okay, so the capacity of any min cut, I'm going to prove this lemma. And it's really something that should already be intuitive, but let me just do it a little bit more formally, because it'll be useful the other way to define all this notation. Okay? So let's think of all the nodes on the left side of this red line as being an ST cut is just a subset of nodes. Okay, it's a partition of nodes, S and T, where this set S has little s in it, and the set big T has little t in it. Okay, so now the capacity of this cut is just the sum of the arcs going from big S to T. So it looks like that. It's some thing where you say, for every edge that goes from S to T, you add up its capacity. Okay, that's the capacity of the arc. So it's the sum of the capacities of arcs that look like this, what's pictured. Okay, so now for a valid flow, the flow out of S is equal to the flow out of little s. Okay? And the flow into T is equal to the flow into T. Let's just say into. So for any valid flow, the flow, it's not even the maximum flow, the flow out of S into T is equal to the capacity for any so that for any valid flow, the most flow you can send out of S is all the sums of these capacities, right? That's the most flow you could send out of big S. Okay? And because the flow out of big S is equal to the flow out of little s, then it says the most flow you could send out of little s is at most the capacity. So this capacity provides an upper bound on the value of any flow. Okay? So the value of any valid flow is at most this capacity. Okay? So this is just really the key to this is this conservation. The flow out of this big set S is exactly equal to the flow out of the little node S, because it's not accumulating anywhere else, or it's not being generated anywhere else. Okay? It's neither accumulating or generated anywhere else in big S. Okay, so the value of any valid flow is at most this capacity. All right? Okay, so now now you know that if you you know that some upper bound on the value of the flow. So let's now think about whether our algorithm actually gets a good value. Okay, so this says there's an upper bound. If you can achieve this upper bound, then you know you're optimal. Okay? Okay, so first, before we do that, let's just do termination, and I think I did that before. It'll terminate, right? Why will it terminate? Right. Because every step, you route at least one unit of flow. And so that says the capacity, the way he argued it is he said the capacity leaving S reduces by 1 every time. So it can't take longer than the total capacity leaving little s, the node S. Okay? So it'll terminate. Flow keeps increasing. It can't increase to forever, right? These numbers are all bounded. Okay. So is it optimal at termination? That's what you need to question. So first, when you want to show something's optimal, you should at least show it stops. Okay? So otherwise, there's a problem. Okay. So now let me give you a break, and then I'll finish this off. Yeah, but you would call it
you have to take like the net flow for anything that isn't the limiting.
You take the net flow, right? So the total flow across the cut is this minus this. Yeah, I should have put that in. Yeah, I'll put it. Yeah.
I think when the student asked the question earlier about like when you have a cut, will like all the pipes you fill to the natural capacity. That's not true because the cut only gives you upper bound, right?
At optimality. It gives an upper bound, yeah. But when you're optimal, it'll give you the right bound.
It'll give you the right number, but not everything heading in the right direction will be filled to the max, right? Because if you just had like
if it wasn't the smallest cut, it won't happen. Yeah, you're right. I mean, so it's a matter of how you quantify it. What you say is there exists a cut where that's true.
yeah.
That's what we're
That would be the opposite, right?
Yeah. For the minimum cut, all the flow will be in the one direction. Right? Does that make sense?
Yeah.
Yeah, I'll mention that. Thank you. Mm-hmm.
So can we use linear programming for this problem? Because isn't there a problem that will give us like a floating point, like a non-integer?
Yeah, it could, but so we're in some sense showing there's an integer solution.
So the constraints force the solution to be integer, even if we were using a linear program.
Well, linear programs are not required to give you integer solutions.
Right.
So it may not give you an integer solution. If you happen to use, so what we're showing is that there is an integer solution. Okay, it may.
Solutions are integers, therefore.
No, they're not all integers, right? So the linear program may not give you an integer solution.
Right.
But I didn't say it had to be an integer.
So it's fine to not have an integer.
It is fine, but you can. The simplex method will give you an integer solution. Not all linear programming algorithms will, but some will. What do you? I know I'm being confusing. There's some quantification issues, right? So you're right. So linear programming itself won't give you an integer
The
solution.
simplex method will always.
Yeah, it will always give you. Yeah,
Oh. Okay.
it will.
In general, if we applied it linear program to this, not using necessarily using the simplex method, we could get this being the maximum. We could get a non.
Yeah, you can get it.
Would be a problem.
It's not necessarily a problem. I mean, it depends on what you want. Is it a problem? It depends on what your output is. You may want. Yeah. Yeah, it doesn't violate any of the constraints we set up, right? Do you just
Give you a non-infinite solution if there are non-infinite ways.
these are the capacities are 1. This is the flow. Yeah, so this is still a valid flow because the flow values are between 0 and their capacity, and the conservation constraints are satisfied. They're all linear constraints. They don't say anything has to be integer. But it does happen to be true that the simplex method will give you an integer solution. Yeah, it happens too. The reason is it gives you something called you know how you have this feasible region? It always gives you one of these. All of these are going to be integer. Yeah, they will be. I mean, it's not totally trivial to see why, but they will. It happens to be the case because each one of these is a solution to a linear set of equations, right? This is just this line intersects this line. Yeah. So now these equations only really have 2 non-zeros, right? They have. Each variable is only in 2 places. Each variable is only in 2 places. Yeah. Any set of equations where only 2 variables, the variable is only in 2 places, has an integer solution. And that's because you remember way back when you did the Gaussian elimination, and you said you could find the solution based on a determinant. That determinant is going to be either plus or minus 1 or 0, because there's only one. Because each variable only appears in 2 places, it has a very simple structure of the determinant. So that's why it will solve you to any vertex solution will be integer. Yeah. It could be that it could output. There exists for example, there exists a solution that looks like this. One. Right? This is a perfectly valid solution, and it's integer. So what happens in this case, is that in the feasible region, there's 2 solutions. There's the solution that goes up, and the solution that goes down. Right? Okay, so let me tell you a joke. I'm not good at this joke, but let me try it anyway, as if I'm good at any of them. But okay, so there's an Englishman, a Frenchman, and a Russian Okay, so don't worry about being PC. The Europeans, they all do this to each other, so it's fine. Um, um, so, um, so they're talking about what is like a real moment or day of happiness. Okay, what's like a really happy thing to do, you know, for a moment or a day. And so the Englishman says, oh, you know, I love to go home and have a great meal that with my wife, and then go sit on my chair and watch the soccer match and have my wife bring me my beer. Okay, so this really makes me. That's just like my perfect day. Okay, so and the French guy says, oh, that's just terrible. My perfect day is I go off on a business trip. I have a wild and torrid affair, and it's so romantic and you know, invigorating and everything, you know, life, you know. And the Russian, he says, no, you guys have, you know, those things aren't even close. So my idea of a happy event is that I'm in bed in my apartment, and it's 2 a.m, and I'm sleeping, and then I hear this rude knock on the door, and I go to the door, and I open the door. There's 2 big official-looking goons at my door, and they're saying, "Oh, we're looking for Ivan Ivanovich," and then I say, "Oh no, Ivan Ivanovich lives over there." This makes a lot more sense if you were born before 1990 and you knew who the KGB was or something. You know? Just a sense of relief, you know? You get it? Okay, never mind. You know? Okay. I thought it goes well with the story from before, you know? Okay, so, all right. So, you know, he's not going to, okay, never mind. Okay. Oh, I see. Okay, so it terminates. Okay, so when are you done? When do you terminate? So when you have this graph, there's no path with residual capacity. Okay, so that's when you terminate. So how do you find paths in this algorithm? How do we find paths in general in a directed graph? Yeah, either breadth first search or depth first search. So let's pick one. So what happens in that depth first search? What happens? Okay, think about what happens in that depth first search when you fail to find a path. When you find a path, what do you find in that depth first search? You start at S, and what do you find? Trying to find a path to T, right? So in that depth first search, what would be reachable? What is depth first search to? It tells you all the nodes that are reachable from your starting point. Explore. You explore from S, and once you return from that explore, you've reached all the nodes you could reach from S. Okay? So if you do find a path, that means you've reached T, right? So if you don't find a path, what does that mean? You didn't reach T, right? Okay, so the depth first search starting at, this is, you know, it's important to get these mechanics. It's very easy, but it's easy to get it wrong. So depth first search only starting at S doesn't reach T. Every step is going to be obvious here, right? But it reaches somebody, reaches some set of nodes. Let's define those to be our big set S. Remember any cut, any ST cut tells us something. So let's build an ST cut from this search. Okay? So the search gives us a set S, and that set S is all reachable from little s. Right? That's what the depth first search does. It just returns as, you can think of all the nodes in there. Okay? So now, no arc with positive residual capacity leaves S. Why do we know that? Right. So S is reachable. So we started at S, and we reach some nodes, right? There's some nodes in our graph. So this is my big set S. Okay? So what I'm saying, what I'm claiming in this statement is that there can't be an arc here where the residual capacity here is greater than 0. All these residual capacities have to be equal to 0. Okay? And residual capacities are either C of E minus F of E, or the residual capacity of UV. It may be that an arc comes into there, and it would have residual capacity if there was flow in this direction. Okay? So there's a residual capacity on this reverse edge, R of E, which is equal to R of UV is equal to F of okay? So there's two kinds of arcs. For this set, for any node in here or node in here, there's either an arc going out whose residual capacity is at most C of E minus F of E, or maybe there's an arc coming in, and you might have residual capacity in this direction if there's flow coming in. Right? Okay, so those are and now I know that all of these arcs have 0 residual capacity, because if one of them had positive residual capacity, what would the depth first search do? It would explore across this node. And this node would then be an S. Okay? So all of these arcs have 0 residual capacity. So all of these arcs have to be full. So this implies that all the arcs leaving S, all the arcs of this form, have F of E equal to C of E. Okay? Because if any one of these arcs leaving S had a lower flow value, you would still have some residual capacity here. Okay? No arcs into S have any flow. All these flows have to equal 0 of this form. Because if any flow was coming in, then you would have a residual arc in the opposite direction with that value. Okay? So the total flow, what's the total flow leaving S? Well, it's all the flow crossing arcs going out, minus the flow coming in. Yeah, you actually have to subtract the flow coming in. So the net flow coming out is the flow going out minus the flow going in. Is there any flow going in? Is there any flow going in? If there was any flow going in, that would mean there would be an arc with flow going in this direction. If there's an arc with flow going in this direction, then that would mean there's residual capacity in the opposite direction. Okay, so there's no flow going in, and every edge going out is at capacity. So the total flow out of S is equal to the sum of these capacities of these edges leaving S. Okay, so the total flow out of big S is equal to the sum over the edges in S cross T of F of E. Right? That's just the total flow out. That's just by definition, that's what the total flow out is. And now F of E is equal to C of E, so it's equal to the sum over E of S cross T of C of E. Yeah. Did you have a question? No, it has nothing to do with incoming. Yeah. Right. It's because there's no flow coming in from those arcs anyway. Okay, so whatever the excess flow leaving this set, now whatever flow leaves this set, where does it come from? It comes from S. So this, again, like we said before, the total flow coming out of this set is actually the value of your flow. So it says here, the value of the flow equals the value of this capacity. Now if the value equals the value of this cut, optimal is less than or equal to the value of this cut for any cut. Okay? So we've produced a flow whose value is equal to the value of some upper bound. So therefore, the flow must be maximum. Okay? And moreover, not only is the flow maximum, the flow tells you it's maximum. Right? Like if I give you a flow, can you figure out whether it's maximum? How would you do that? One way you can do it is you find a cut whose value is equal to the flow. Okay? So how would you do this? If I give you a flow and I just said, I don't care, you don't need to compute the max flow for me, you just need to tell me whether this flow is maximum. So this is really important, right? This is why, right, that's almost it. Well, you just run one iteration. What did this proof do? It said, well, I run depth first search. I look at Ford Fulkerson. I run depth first search. I look at the reachable nodes from S in the residual capacity. Given the flow, you could define a residual graph. It's easy, right? For each edge, you just define the arc to have capacity C of E minus F of E. And they're put in the reverse. You run depth first search, you find an S. And now that S is going to be, the value of the flow is going to equal the capacity of that cut, if it's a maximum flow. If it's not a maximum flow, what happens? Anybody? Yeah, T is reachable, and you could actually increase the value of the flow. Okay? So the cut is minimum 2. And moreover, the algorithm provides both. Okay? So did Christos tell the story about the railroads in Russia? Did he tell you the story about the railroads in Russia? Okay, yeah. So this is the point, right? The Russians were trying to ship flow, and the Americans were trying to do nasty things. So, okay, right? They were trying to find the minimum cut. Same algorithm. The same algorithm provides both. At the end, you get a flow, and moreover, you get a proof that it's maximum. Right? And that's really, really nice, especially if you're a defense contractor. Or if you have to, not nice if you're a defense contractor, if you have to use a defense contractor. Because what they do is they give you a solution, and you want to be able to check it fast. And here, with just one depth first search, you can check and see if it's optimal. Right? So they give you a flow, and one depth first search, and you know. Right? So this is a really useful thing. Do people do this in their code? When you write a sort program, you know what you should always do when you write a sort program? Yeah, you should leave the check in, because it's free. Right? What is the check for sorting? What's a really cheap check to make sure your list is sorted? You just scan and make sure everybody's less than the person next to them. Right? Just leave it in your code. It doesn't matter. You should just put it in. It should just be there because it's free anyway. Okay? If you do your test cases, all your test cases, and you think your code is correct, maybe you just had bad test cases. Maybe later the data comes out. At least you have a warning in your log. You probably shouldn't crash, but you need to do what to do when you do the check. This is the same thing. Here you know you're optimal. You should, and this is a very important sort of concept in computer science, is if you have a solution, can you do a quick check to make sure it's right? Okay, so this thing does. Linear programs have that nature. They at least you can check the constraints. Now, For this particular linear program, you can actually get a proof that it's optimal. Okay? And in fact, for any linear program, which we're going to talk about on Thursday. So any flow is less than any cut. So this flow is equal to this cut. So this maximum flow and the minimum cut. Why is this flow maximum? Because this flow equals the value of its upper bound, of an upper bound to it. Why is this cut minimum? Because this cut equals the value of its lower bound. Right? An upper bound for one thing provides a lower bound for the other thing. So since we know flow is maximum because it can't be any larger. It's this value and can't be any larger. Okay? Now we know this cut is minimum because it's this value and it can't be any smaller. Okay, so it's a proof of both things. Yeah. Yeah, it does, right? It's constructing the flow. The flow is these FE values. Yeah, that's the output, just the FE values. It's an assignment of value to each edge, right? Okay, so this is a celebrated theorem. I should play music because we need to celebrate. Okay, it's better with music, but okay. It was a big deal. Okay, so let's see how efficient it is. So here's a network. Okay, so how long? It's 4 nodes. Okay, we saw this before with Dijkstra, right? We have a small network just with big numbers, but we want the running time to be sort of proportional to the number of nodes, not to the size of the numbers, right? So what does Ford-Fulkerson do? It could do this. That could be its first path. Let's see how many iterations it takes. Any guesses on how many iterations it takes? What is that, 100,000? Okay, so now I'm at... Okay, so you get the idea, right? Okay, so I should change the numbers, but okay, then I'm going to do it again. Right? So it could take a long time because like I said, I don't, you could forgive the poor depth first search, right? It doesn't really know what's going on. It's just sort of moving around trying to find a path. So it's clearly doing the wrong thing here, but it doesn't really know. It doesn't have much information, right? It doesn't know what it's supposed to do, and it keeps doing this and goes back and forth, and it's going to take 100,000 iterations for this little bitty example for Ford-Fulkerson. Okay? So can anybody think of something that might be better than depth first search? This is an easy one. Yeah. Okay, so now we can do breadth first search. Somebody suggested this last time. Okay? So breadth first search works. Okay, but it's not so easy to see why it works. So this is the Edmonds-Karp algorithm. Karp is a professor here. So you do breadth first search. Okay, so I can't give you the analysis completely because we don't have that much time. But in algorithms, you gotta know what happens in this thing. Something terrible happens. You push across an edge, then you unpush across the edge. Then you push across the edge, and then you go the other way. 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 You look at the same darn edge over and over and over and over and over again. Right? That's the problem here. Okay? So this is what's happening here, right? You push one way, you push the other way, back and forth and back and forth. So when you do breadth first search, you're still going to push it back and forth. There's not much you can do about it. This is one of the major questions, how to get this very efficient. You always push back and forth. So, but we can show that you only do order V times E augmentations. Okay, so that means you push back and forth across an edge only more or less E times. Okay? So the point is the following. So what the idea is, in breadth first search, you have a notion of progress. As you fill up the network, nodes kind of get farther and farther away from the sink. The source does. First you push flow along the shortest path, So you saturate all the shortest paths. Okay? Then you push along longer paths, and then longer paths, and then longer paths. And every time your distance to the sink for any node is growing. Because you're always sort of finding the shortest path and making sure that's full. Okay? So this distance is only growing for any node. Okay? And now, if you're pushing along depth first search, you're only getting closer to the sink. Every time you go from somebody who's far from 1 unit further from the sink to 1 unit closer. So you're only pushing downhill. Okay? So that's what happens in this algorithm. You're only pushing closer. So you could only push flow, you can only route flow on UV if D of U, if U is farther than V, actually strictly farther, it shouldn't be equal. So you can only push downhill. Okay, so that's one thing. And then now you can only push in the other direction. So the problem is when you push in both directions. If you push in one direction, that's sort of fine. If you keep doing it, at least you're not going back and forth and back and forth. But you can push in the reverse direction, but then D of V has to be less than D of U. Okay? So the maximum value, the maximum distance to the sink is at most V, right? You can't, once you're farther than V away, there's no path to the sink. Distances only go up, and that's the key thing. When you route along shortest paths, the distances of the sink only go up. Okay, because you're saturating the short paths. So now all the paths that remain in the residual graph are only longer. Okay? So now every time you augment, you fill up one edge, right? You make sure that edge no longer has any capacity in this direction. So the only way you can have that edge back in your network is in the opposite direction. And you can't push along that until the other endpoint raises. Okay? So since the max height is only V, and now each edge only appears at each distance once, and every augmentation removes an edge. So the edge can remove, each edge can be removed V times. So there's basically, in some sense, V times E removals. You can't put, once the edge is saturated in this direction, you can't ever push on it again. So it's gone until the nodes change. Okay, so there's order V times E removals. Each augmentation does a removal. So it's order V times E squared. So this looks terrible, right, compared to Fuller-Fulkerson, which just says, oh, okay, it's just the maximum flow. It's the value of the maximum flow. It's linear in the value of the maximum flow. But for this little network, right, this 4-node network, it's not gigantic, right? It's not exponential in its size. So this is the beginning of sort of a sequence of things to make max flow much more efficient. So, okay, so I just wanted to show you that. Okay, so max flow, the greedy algorithm, this is kind of the first really sophisticated sort of algorithm we're doing. Okay, so it says you really have to, things are going back and forth. But there's actually a simple solution in this case, right? This residual network. Okay? Yeah, you can reverse the old decisions. Yeah, this is a place where you could try to do the greedy thing and then reverse it a little bit. So it's a nice paradigm in that sense. So the optimality is you have an upper bound on the optimal, which is a cut. And then you can find a flow and a cut with the equal value. And this is a big deal, that the optimal, when you're done with the algorithm, you don't have to rely on somebody implementing this algorithm correctly. When they give you an answer, you can check it, right? Very, very efficiently. It's a fancy algorithm that takes cubic time, but in the end, your check for it is linear time. So this is like really a big deal. You should always write code. When you have a cheap check, you just leave it in there. Ship it with the code in there. Okay? Because you're going to be fixing it out there in the world. Okay, and you want it in the log line. Okay, this happened. Okay, so that's it.